Okay, I'm gonna go to bed, so I'm gonna do this quick. Hey guys, this shit's cooking. Hey guys, my name's Yabi. This is gonna be a thing I do now where I explain some random architecture topic that I read or done through research or some project for like 10-ish minutes. I'm gonna expect some like baseline level of architecture knowledge, but it's really just gonna be me talking about whatever I want for like 10 minutes. Yeah, that's about it. Then after, I'm gonna shoot this shit for like a couple of minutes. Maybe reason I'm doing this is so I can actually like learn these topics a lot better. I say the best way to learn something is by doing it, but I'm not writing an out-of-order processor. So second best way to learn something is by explaining it to someone. And the only person who wants to hear me ramble about architecture is probably my phone camera and some random DV dude in a foreign country. So yeah, let's get started. Today we're going to be talking about register renaming and dealing with false data dependencies to actually leverage instruction level parallelism and flipping like a superscalar or an out-of-order processor. So yeah, for background, I implemented a superscalar processor without out-of-order execution or register renaming. Didn't really get that many seconds off the critical, not many seconds off the critical path. I really didn't get that many seconds down like the total execution time of the program we were running on it because I didn't implement these things. So yeah. I also one-take Jake all of this. Like I point the camera at me and I just click record. So if you're using this is not like material I would use to study for a test. I will link the material that I read / learn from in the description if you actually want to learn it. This is mainly for my own sake of learning. Okay, so read after writes. Read after writes are the only kind of real data dependency, i.e. instruction 2 cannot execute without instruction 1's execution being completely done, i.e. the write back stage completes and it writes it into the source register. And it's pretty clear why, because if the value in x1, when this guy hits its decode stage, which is going to be like when we're here, this guy hasn't hit the write back stage yet, instruction 1. So x1 doesn't have x2 plus x3 in it. It has some like garbage value. It has like dead beef in it. So this is going to go on with like dead beef instead of like 9, and then you hit write back and it writes it back to the source register. It's wrong. Your ASIC's a piece of crap. You lose like millions of dollars in the amount of time it took you to print out the chip and time and money. Your company goes bankrupt. You sell it for cheap to AMD. Your IP gets open sourced and now you can't pay child support. What a cruel life. So, the way you fix this is by bypassing or just like stalling out. So it's very similar if you had a superscalar processor or even an out of order. Well, with an out of order it'd be a little different. It would just like sit in the reservation status for a bit. But yeah. So that's a real data dependency. Like we can't get around it. But then there are also false data dependencies, like right after reads or right after writes. So they're pretty self-explanatory. Right after read is where, like, let's say we write some data into x1 and then we read x1, so that we have like a store word, right? And then in instruction 3, we write to x1. You can imagine where this can go wrong when you're trying to do some like instruction level parallelism, like some like parallel execution things, where like both these, like you have the hardware, like you have 2 instructions happening at once, and like your circuit, like your chip has multiple ALUs, so it's able to do multiple instructions at once. Where like having instructions that are compiling at the exact same time could cause some unplanned unplanned execution in your processor, because it's essentially like let's go back to like system Verilog. Let's talk in an RTL, like some HDL. It's essentially like you have your flip flop, and these 2 if statements aren't mutually exclusive for some god knows why. Well, we know the reason. For some reason. So you have no idea what's going to be in x1 next cycle, because you're doing a non-blocking assignment to that register. You don't know what's going to happen. Like, I guess like with some like directives in HDL, you can make it so like, well, A, your HDL will give you a warning if you do this, but B, like maybe with some HDL, like this happens first and this one happens and this one gets annoying. But in a general case, you don't know what happens. You have to confirm that these if statements are mutually exclusive, because if you do both these writes at the same time, you don't know who's going to win out. And that's why this is so bad, because what if when you're executing these at the same time, you're essentially opening yourself up to this block of HDL code, and you don't know what's going to happen if, like, this guy, the younger instructions ends up completing its execution first. Then X1 might not have this value from instruction 1 that you wanted, and now your processor doesn't work, and then your chip company ends up failing because you lost $3 million in your poor ASIC tape out, and then... Anyways, so this is fixed by register renaming. Right after it's kind of like same circus for monkey. So register renaming is kind of what it sounds like. Oh my god, my problem's fixed. Yeah, that's about it. There's a little bit more nuance into it that I'll go into, but this is the solution your compiler will end up doing. I won't necessarily like compile the bad code to change it. Your compiler will try its best to make source registers be from different architectural registers, because remember, your CPU will only expose this architectural registers to Cody bit code land. That's why, like, actually I'm not going into that. So like, let's say you're working with like RISC-V, you only have 32 architectural registers. But let's say you're like running RISC-V on like the M1 Apple chip, which has like 600 physical registers. I think, something like that. I don't know these things off the top of my head. I'm not that big of a nerd. So your compiler won't know about those physical registers, but your hardware, you, the chip designer, do know about them. So what you do is, and we're going to do something that's kind of like similar, well, not similar, it really is just like tomasulus algorithm. So what's going to happen is your instructions are going to go into what's called the reservation station, which is just where it like fetches and stores instruction operands like right when they're available. So source operands can either point directly to the source register, or it can point to something in the reservation station. When would it point to something at the reservation station? It would point to it in a situation like this one, where this is the exact same. Anyways, it would point to it in a situation like this one, where X1 will never actually make it out of the reservation station, because at the end of the day, the guy who's going to be written to the actual like CDB common data bus, or like that's actually written to the architectural map table, is going to end up being this later instruction. This instruction should never see the light of day. However, this instruction is going to need a read from this instruction. This is the case where you're actually going to end up reading from the reservation table. Meanwhile, this instruction is just going to go down the pipeline, and you can like pretty clearly imagine it. This is just like setting ready valid bits. So before it goes into the reservation station, we're actually going to point where that source operand. We're going to change where that source operand points to. Where can it do that? You have a free list of all your free registers. You have the reorder buffer like looks at these things and uses them to decide what order it should execute these commands in. That way it can leverage as much instruction level parallelism as possible. Because remember, you have 3 ALUs. Your end goal is to execute as many instructions at the same time as possible, so your processor can go zoom. So at like a higher level, trying not to like point at like the ready valid bits, because these are also very implementation like basic. If you look at like out of order RISC-V, like RISC-V boom, they'll dude, give me the documentation. RISC-V boom. If you look at something like RISC-V boom, do not show me code. Okay. Yeah. I believe in myself. Anyways, if you look at something like RISC-V boom, they have like a way different way of deciding how they end up ordering instructions. They have like a distributed scheduler. They'll have their own way. Yeah, they have like a reorder buffer, and it's also a raw, but they do some things like slightly differently. I think the original one used something called like a RAT, which is like a rename map table. But at the end of the day, it's like this core high level idea of you have architectural registers and you have physical registers. And what would end up happening is if you have a false data dependency, whatever like the most latest command is, you end up pointing that to a different physical register. That way you can still execute the command at the same time as the first command, But any other things that refer to what was tagged by the first command, i.e. like anything that's using, so like instruction 2 here, which is reliant on whatever is stored in instruction 1, we'll just have a little bit thing that say, oh, hey, I'm talking about this architectural register. Then, or this version of the physical register. Then anyone that relies on this one can just say, hey, I'm talking to this completely different physical register. So X1 can point to like register P5 here, and you'll have a tag for it. And then this can point to like register P6. And then this one also tag to register P5. And then the most recent, you'd also have to tag like the order in which they come in, because the most recent one is going to be the one that actually ends up getting written out to like your write back stage to the end source operator. But like, it still goes back to that base sentence of you have your architectural and your physical registers, and you just change the pointer of the physical register for that specific command. And then, yeah. But you're still able to deal with write after reads, because you have this sort of reservation status, or like this ready, like rename valid bit or whatever. The main difference between tomasulus, oh, I pronounced it right, tomasulus algorithm and scoreboard is just the tomasulus just has like this, the control logic is keeping track of the reservation status. Meanwhile, or the control logic distributes from the reservation status, but with the scoreboard, the scoreboard kind of just does all the work. And once again, like, there are so many different ways that this ends up being implemented, but it's still that baseline thing of just like change the pointers to the physical registers and have some bits keeping track of what instructions point to what version of an architectural register. Yeah, and now you can process and do the math for as many instructions as you want and just store them in different places. That way these can all, well, this can't execute without this, but these two can end up executing at the same time in an out-of-order processor, because this guy's no longer talking about X1 P5s. Now he's got changed to X1 P6. And then obviously you'll have like a retire stage that like talks to both the free list and the architectural map, because if you ended up changing a pointer to like that one example that I had like over here, if it changes from like P5 to P6, you now need to change it to here to P6, and you now need to say that, hey, P5 is now free. Yep, that's register renaming. Hopefully I'll get better at explaining things, but I don't know. Okay, now for my 5 minutes of shooting the shit, I will talk about, I have like a list of these. Can I get a fry? I like this one. So, okay, this is gonna be like a riff off of like, can a nigga borrow a fry? I think that inherently is stupid, but I think the idea of like, can I get a fry is also stupid. Like, because I'm not trying to be greedy. Like my mom will hear me go on this rant and she'll be like, yeah, we share your food, like love everybody. That's not the issue. Like if I'm eating some like jejavois, like cool pasta, like okay, whatever. Like you can have some. I know you want to know what it tastes like, but like you know what a French fry tastes like. You know what a Dorito tastes like. And then like my qualm isn't with sharing the food. I don't care about sharing the food. My qualm is with trying to understand what is going on up here. Because what do you get out of eating the fry? You are not going to be satiated by like the 7 calories in the fry. If the 7 calories in the fry are what like make or break your satiation. Also, fries aren't that calorically dense either. Potatoes are, but like they're just fried in damn oil, so they're not that calorically dense. So you're not gonna get full from it. You're just gonna like eat it and then go like, oh. So there are like two worlds here, right? One is you're not thinking and you're gonna want to go for the second. Like you think that will make you full and it doesn't, and then you like it's in your mouth and you're craving it because you're a little rat boy, little almond boy, and you want to eat more fries. So then you end up taking more fries. Now you eat half my damn fries, and that's not the issue. If someone saw me eating fries and was like, "Hey, can I get like some of those fries? Not a fry. Can I get some of those fries?" Sure, you're eating to be full. You're eating because you really want to cement the taste. But, well, not cement the taste. That's a different thing. But if you're saying, can I get a singular fry? What do you gain out of that? Because you're either stupid and you're going to eat multiple fries, or you're just going to, like, what? Eat one, then be like, I'm full. And no, you're not going to be full. You're not going to get anything out of it. It's not going to taste good. It's a damn, like, 2-cent French fry. Potatoes are 99. Yeah, like 2-cent French fry. Like, what do you gain out of that? Like, this applies to most things. Like, can I get a chicken nugget? Like, a singular chicken nugget, that's going to hold you over. Maybe I'm just big, but like, I could eat like 20 and still be hungry. Like, And that makes it sound like I'm being greedy about the food, but I'm not. I'm just like, there's just some inherent stupidity in saying, can I get a single fry? And like, that's one thing I appreciate. Like, when my mom takes my fries, she takes a handful of them. She gets multiple of them. And that's not dumb, because you're eating to be full. Eating multiple fries is what actually is gonna make you full. Also, can you even taste it when you eat a singular fry? What is a sip of this tea isn't, I'm not gonna go, and be like, like, I really get it. No, you're gonna need to have multiple sips. Like, the flavors need to compound. Like, the umami, it exponentially grows. It doesn't just, like, linear, like, even if it linearly grew, like, one, like, little tick isn't even gonna help you out here. I don't think it exponentially grew. I think I was talking on my ass, but, like, it's gonna grow out literally. Like, you need to eat more. You can't just have one and be like, that's it. Like, I swear to God, like, I've never heard of someone say the first bite of a burger is the best. It's gonna be, like, the third, and you can see me on that one, too. But, can I get a fry is just so dumb, because what do you get out of it? Yeah, I didn't expect that one to be so aggressive, but I just think it's so stupid. Like, what do you get out of eating a singular french fry? Nothing. Yeah. I think that was enough shit shooting for the day. I think that's it. I'm probably gonna, like, put whatever papers I read to learn this stuff in the description, and also I'm gonna source, like, risk by Boo. They always name their process cool. But yeah, next time I'll pick a chapter out of quantitative approach. See you.